Welcome to Orbit Observer. Settle in, get comfortable, let your shoulders drop, and let the day you just had begin to loosen its grip, one small thread at a time. There's nowhere you need to be right now, nothing you need to solve. For the next little while, the only thing on the agenda is a slow drift outward, away from the noise, away from the warmth of the sun, out past every planet you learned as a child, into the cold and quiet dark, where the light is thin and the worlds are strange. And there, waiting for us in that darkness, is one of the strangest worlds of all. I want you to picture a single night. The date is the 21st of January in the year 2017. On Earth, it's an ordinary winter night in Europe. In observatories scattered across the continent, telescopes are open to the sky, their domes rolled back, their mirrors cooling in the dark, all of them pointed at the same faint, unremarkable star. To the eye, nothing about that star stands out. It's just one more distant pinprick among millions. But the astronomers watching it know something the rest of the world does not. They know that for a few precious seconds, that star is about to disappear. Not because it's dying, not because a cloud is passing. It's about to disappear because something is going to slide silently in front of it. A dark, cold, egg-shaped world, so far away that no telescope on Earth can see it as anything more than a single dot of reflected sunlight. And as that world crosses in front of the star, its shadow will race across the face of the Earth, sweeping over those waiting telescopes like the shadow of a hand passing over a candle. The astronomers have set up their instruments in a line, spread across different cities and mountaintops, precisely because they want to catch that shadow at slightly different moments and stitch the timings together. They are, in the most literal sense, waiting for a light to go out. And it does. At the appointed instant, the star winks off, just gone, as if someone has quietly pressed a thumb over it. A few heartbeats pass, and then it winks back on, exactly as before, patient and unbothered, as though nothing happened at all. To anyone standing outside, glancing up, there would have been nothing to see. But inside those domes, in the flickering numbers scrolling down the screens, in the dip of a line on a graph, something extraordinary had just been recorded. Because when the astronomers went home and gathered all their measurements together and laid them side by side, they found something in that flicker of vanishing starlight that no one had predicted. Something no one had even thought to look for. And to understand why that discovery mattered so much, and why it made a room full of scientists go quiet, we first have to understand the world that cast that shadow. We have to travel out to meet it. Its name is Haumea. And Haumea is not like the planets you know. Let me tell you the single strangest thing about it first, because everything else flows from this one fact. Haumea spins. All planets spin, of course. Our own Earth turns once a day, a slow, stately rotation that gives us our sunrise and our sunset 24 hours from one noon to the next. Jupiter, the giant of our solar system, spins faster, turning once in about 10 hours. But Haumea makes both of them look half asleep. Haumea completes one full rotation in about 3.9 hours. Not a day. Not 10 hours. Under 4 hours. If you were standing on its surface, the sun, tiny and distant as it is out there, would rise and set and rise again before you'd finished a single afternoon nap. It is spinning faster than any other large body in the entire solar system. Nothing bigger than a small city turns as quickly as this whole world does. Now hold that thought, because here is where it gets beautiful. When something spins that fast, the spin does something to its shape. Think about a pizza chef spinning a lump of dough on his fingertips. When the dough is still, it's a round ball. But as he spins it faster and faster, the dough flattens, it stretches, it flings itself outward at the edges, pulled by the spinning. The same thing happens to a world. Haumea is spinning so violently that it has been stretched. Its own rotation has pulled it out of the round, comfortable shape we expect a planet to have, and drawn it into something long and oval. Something that looks, honestly, like a giant cosmic egg. Or if you prefer, imagine a rugby ball or an American football tumbling end over end through the dark. That is the true shape of Haumea. Not a globe. An egg. A world stretched by its own dizzying spin. And this isn't a small stretch, a subtle bulge you'd need instruments to notice. It is dramatic. When the astronomers finally measured it properly, using that very shadow from that January night, they found that Haumea is about 2,320 kilometers long along its longest axis. But across its shortest direction, from pole to pole, top to bottom, it is only about 1,000 kilometers thick. Sit with those two numbers for a moment. It is more than twice as long as it is thick. Imagine an egg where the length is double the width, and you're beginning to see it. This is a world that has been genuinely deformed by its own motion, elongated into a shape that no calm, slow-turning planet could ever hold. Scientists have a precise name for this shape. They call it a triaxial ellipsoid or a Jacobi ellipsoid. Those are technical terms, and they sound like something from a dusty textbook, so let me hand you a simpler picture to hold on to instead. Think of it as a body with 3 different measurements in 3 different directions. A perfect ball is the same width no matter how you measure it. A slightly squashed planet, like our own Earth, is a little wider around the middle than from top to bottom. But Haumea is different in all 3 directions at once, long one way, medium the other way, short from top to bottom. Like an egg, or a smooth river stone, or a lozenge of stretched taffy frozen solid in the deep cold. That's a Jacobi ellipsoid, a world with a shape that only extreme spinning can carve. And there's a quiet menace hidden inside that fact, which makes it even more remarkable. Haumea is spinning right at the edge of what it can survive. If it were turning much faster than it already is, the spin would win. Gravity, the gentle glue that holds a world together and pulls it into a ball, would no longer be strong enough to hold that stretched, straining shape in one piece. The world would begin to come apart, flinging material off its long ends into space. Haumea sits right at that threshold, right at the limit, balanced on the knife's edge between staying whole and tearing itself to pieces. It is, in a sense, a world spinning as fast as it possibly can without flying apart. And it has apparently been doing this delicate, dizzying balancing act for a very, very long time. So already, before we've gone any further, we have a world that breaks the rules. A world shaped like an egg, a world spinning under 4 hours, a world balanced at the very edge of its own destruction. And here is the question that should be forming in your mind, the one that turns this from a bag of odd facts into a genuine mystery. How on earth do we know any of this? Because here is the thing you must understand about Haumea, the fact that makes everything about it so astonishing. No one has ever been there. No spacecraft has ever visited it. No probe has ever flown past it and turned its cameras toward it. There has never been a mission to Haumea, not one, in the entire history of space exploration. We have sent machines to Pluto, We flung a small, piano-sized spacecraft, New Horizons, across billions of kilometers, and it swept past Pluto and gave us those glorious close-up photographs of ice mountains and frozen plains. But Haumea? Nothing. It has never had a visitor. It sits out there in the dark, unbothered, unphotographed, unmet. And yet we know its shape to within kilometers. We know how fast it spins. We know what its surface is made of. We know it has moons. We know, as we'll come to, that it wears a ring. All of this we know about a world we have never seen up close. A world that to our very best telescopes is nothing more than a single, faint, trembling point of light. That is the real story here. That is the thing I want you to carry with you as we drift deeper into the dark tonight. Everything we know about Haumea, every single fact, was pried out of that one dot of light and out of the shadows it casts. We reconstructed an entire alien world from flickers, from the way its brightness rises and falls, from the way a star blinks out behind it for a handful of seconds. We built the portrait of a world we have never touched entirely out of light and shadow, and once you understand how they did it, the whole thing starts to feel less like astronomy and more like a detective story, solved from 4 billion kilometers away. So let's begin to solve it. Let's go and find where this strange egg-shaped world actually lives. To get there, you have to leave the warm, familiar inner solar system entirely behind. Picture yourself lifting away from the sun. First, you pass the rocky inner worlds, Mercury and Venus, our own blue Earth, rusty Mars. Then the Great Gap, and beyond it the giants, Jupiter and Saturn with its rings. Then Uranus and Neptune, those two distant ice giants, glowing a faint, cold blue. Most people, in their minds, stop there. Neptune, they think, is the edge. The last planet, the end of the line. But it isn't the edge at all. Because past Neptune, the solar system doesn't stop. It opens up into a vast, cold, sparsely populated frontier, a great ring of frozen worlds and icy debris that circles the sun far, far beyond the planets we grew up naming. This region has a name. It's called the Kuiper Belt. The Kuiper Belt is a wide, donut-shaped zone of icy bodies out beyond Neptune's orbit, where the leftover building blocks of the solar system still drift, deep frozen, in the dark. Pluto lives here. So does another dwarf planet called Makemeke, and another called Eris. And so does Haumea. These distant frozen worlds are called trans-Neptunian objects, which is a grand phrase that means exactly what it sounds like. Objects beyond Neptune. Bodies whose entire lives play out past the last of the great planets, in a place where the sun is no longer a warming presence, but merely the brightest star in a very cold sky. And when I say cold, I want you to really feel how cold. Out where Haumea drifts, the temperature is somewhere around 50 Kelvin. Now, Kelvin is just a way of measuring temperature that starts counting from the coldest anything can possibly be, from absolute zero, the point where all motion stops. 50 Kelvin, in the numbers we're more used to, is about minus 223 degrees Celsius. Minus 223. There is no word warm enough and no coat thick enough to make sense of that. It is a cold so profound that the very idea of liquid water is absurd. Out there, water isn't something that flows. Water is stone. Water is rock. Ice on Haumea is as hard and permanent as granite is here on Earth. The whole world is built partly of frozen water, so cold it behaves like bedrock, and it has been that way, undisturbed, for billions of years. Why is it so unimaginably cold? Because it is so unimaginably far. Haumea orbits the Sun at an average distance of about 43 times the distance between the Earth and the Sun. Astronomers use a handy unit for these distances. They call the Earth-Sun distance 1 astronomical unit, 1 AU. So the Earth sits at 1 AU, and Haumea drifts at somewhere between about 43 and 50 AU, depending on where it is in its long, slow loop. Right now, in our own era, it happens to be near the far part of its path, roughly 50 AU from the Sun. 50 times farther from the Sun's fire than we are. And distance does something cruel to sunlight. Light spreads out and weakens the farther it travels, and it weakens far faster than you might guess. Out at Haumea's distance, the sunlight is only about 1/2500th, as strong as the sunlight that warms your face on a summer afternoon here on Earth. 1 part in 2,500. If you could stand on Haumea's surface and look up at the Sun, it would not be the great golden disk we know. It would be a single, brilliant, piercing star, far too bright to look at directly, yes, but tiny, a hard little diamond of light in a black sky, giving almost no warmth at all. Noon on Haumea would be dimmer than a moonlit night at home. That is the twilight world we're visiting tonight, a place of permanent, frozen dusk. And it takes its time out there, moving slowly through that dusk. Because it is so far from the Sun, Haumea's orbit is enormous, and it crawls along that vast path at a stately, unhurried pace. One single trip around the Sun, 1 Haumean year, takes about 284 Earth years. Let that number land for a moment. 284 years. The last time Haumea was at the exact point in its orbit where it sits tonight, the American Revolution had not yet been fought. Entire empires have risen and fallen, whole centuries of human history have unspooled, generations upon generations have been born and lived and died, all in the time it takes this one distant egg-shaped world to make a single loop around the Sun. It moves so slowly and so far away that from our brief human vantage point it seems almost to hang motionless in the dark, a single patient traveller on a journey longer than any nation. And its path is not a neat, tidy circle either. Haumea's orbit is a bit stretched, a bit lopsided, an ellipse rather than a perfect ring. At its closest approach to the Sun, a point astronomers call perihelion, it comes in to around 35 AU. At its farthest, at aphelion, it swings out to around 51 AU. So over the course of one of those enormously long years, it drifts inward and then back outward again. Though even at its closest, it never comes anywhere near warm. Its path is also tilted, leaning at an angle of about 28 degrees compared to the flat plane where most of the planets orbit. So Haumea doesn't just circle the Sun. It circles the Sun on a slant, rising up above the main disk of the solar system and then dipping back down below it, an outsider even in the geometry of its travels. A world that does everything at its own strange angle. So this is our subject. Let me gather it together for you so you can hold the whole picture as you rest. Out beyond Neptune, in the cold frontier of the Kuiper Belt, drifts a world called Haumea. It is a trans-Neptunian object, a frozen leftover from the birth of the solar system. It sits some 50 times farther from the Sun than we do, in a cold of around -223 degrees, bathed in a sunlight so faint it would seem like starlight. It takes nearly 3 centuries to circle the Sun once, moving along a tilted, stretched orbit all its own. And it spins, faster than any other large world we know of, once every 3.9 hours, so fast that it has stretched itself into the shape of an egg, over twice as long as it is thick, balanced right at the edge of flying apart. And we know all of this, every last detail, without ever having sent a single machine to look at it. We know it from light, from shadow, from a single star blinking out on a winter's night. Now, I promised you a detective story, so let me start laying out the clues, because the way we came to know Haumea's shape is itself a small marvel, and it begins not with that dramatic shadow in 2017, but years earlier with something far quieter. It begins with a flicker. When astronomers first began watching Haumea carefully, back in the early 2000s, they could not see its shape. Remember, to even our finest telescopes, Haumea is not a disk. It is not a little ball you can measure with a ruler. It is a point, a single dot of light, no bigger in the eyepiece than any faint star. You cannot look at a dot and say, "Ah, that one's shaped like an egg." A dot has no shape. So how could anyone possibly have figured out that this particular dot was a stretched, spinning ellipsoid? The answer is that they didn't look at its shape. They looked at its brightness. And they watched it over time. And what they noticed was that the dot was not steady. Its brightness rose and fell in a smooth, regular rhythm, dimming and brightening and dimming again, over and over, with a cycle that repeated every few hours. The little point of light was pulsing, like a slow, faint heartbeat. Now think about why that would happen. Imagine that egg-shaped world tumbling in space, turning on its axis. When its long side is turned toward you, you're seeing a big, broad face of it, catching and reflecting a lot of sunlight, so it looks a little brighter. But then, as it spins, that long side turns away, and you find yourself looking at the narrow end of the egg, a smaller face, catching less sunlight, reflecting less back to you. So it looks a little dimmer. Turn again, and the broad side swings back into view. Brighter, turn again, narrow end. Dimmer, a spinning egg, seen from far away, would appear to pulse in brightness, growing brighter and fainter in perfect time with its rotation. Which is exactly what the astronomers saw. They plotted this rise and fall on a graph, tracking the brightness over the hours, and the wiggling line they drew has a name. They call it a light curve. It is, quite simply, a record of how an object's brightness changes over time. And Haumea's light curve told them two enormous things at once. First, from how long it took to go from bright to dim and back to bright again, they could read off exactly how fast it was spinning. That's how they got the 3.9 hours. The rhythm of the flicker is the rhythm of the spin. And second, from how much the brightness changed, from the depth of that dimming. They could work out how stretched it was. The brightness only changes by a certain amount, about 3/10 of a magnitude, which is astronomers' language for a modest but very clear and measurable swing. A perfectly round ball would show no flicker at all, because every face it turns toward you looks the same. A slightly oval world would flicker a little, and a dramatically stretched, egg-shaped world would flicker a lot. From the exact size of Haumea's flicker, they could deduce just how egg-shaped it had to be to produce that much variation. Isn't that a wonderful thing to consider? They had never seen its shape, they had only ever seen a dot. But by patiently watching that dot brighten and fade, hour after hour, they read the spin and the stretch straight out of the pulsing light. It's a little like standing far too far away to see a lighthouse itself, but watching its beam sweep past you, and from the timing of the flashes alone, working out how fast the great lamp is turning inside. The light carries the secret. You only have to be patient enough and clever enough to read it. And that was the state of things for years. We knew Haumea was fast. We knew it was stretched. We had that flickering light curve, and from it a good, confident guess at the spin and a rougher sense of the shape. But a light curve, for all its cleverness, has limits. It tells you the proportions of a world, how much longer it is than it is wide, but it struggles to nail down the true size, the actual number of kilometers, with real precision. For that you need something sharper. You need a ruler laid across the world itself, and in the dark of the outer solar system there is only one ruler sharp enough for the job. It is the very thing we began this journey with. It is a shadow. Because here is the beautiful logic of it, the thing those European astronomers were counting on that January night. If you cannot make your telescope sharp enough to see a distant world as a disk, then you let the world draw its own silhouette for you. You wait for it to pass in front of a star. And when it does, the star's light is blocked, and the duration of that blocking, the exact number of seconds the star stays hidden, tells you how wide the world is along the path the shadow took. A big world blocks the star for longer, a small one for a shorter time. It is the simplest measurement in the universe in a way. You are timing a shadow, but timed precisely enough from enough places at once that shadow becomes a ruler accurate to within a kilometre, laid across a world 4 billion kilometres from home. This is what astronomers call a stellar occultation. Occultation is just the formal word for one thing passing in front of and hiding another. The star is occulted, hidden by Haumea. And a stellar occultation is, quite genuinely, the single sharpest tool we have for measuring a small, distant world, sharper than any photograph, sharper than any telescope image, because it sidesteps the whole problem of not being able to see the thing directly. You don't need to see Haumea, you just need to watch the star it hides and time the darkness and let the geometry do the rest. But it is not easy. Not remotely. To catch a stellar occultation, everything has to line up. Quite literally. First, you have to predict, months in advance, that this particular faint, distant, egg-shaped world is going to pass directly in front of that particular star, as seen from Earth. And Haumea is small, and its exact position is known only so well, and the star it must hide is just one of countless stars in the sky. The alignment has to be nearly perfect. The shadow, only a couple of 1,000 kilometers wide as it falls on the Earth, miss the prediction by a hair, and the shadow lands in the ocean, or on the wrong continent, or misses the Earth entirely. Then, even if you predict it right, the shadow crosses the Earth in seconds, racing along at tremendous speed, so you have one chance, one single fleeting pass, no do-overs, and you had better have clear skies. One cloud over your telescope at the wrong moment, and the whole thing is lost. So the astronomers did the only sensible thing. They didn't rely on one telescope. They set up many, spread out across Europe, more than a dozen observatories, deliberately scattered across different countries and different latitudes. That way, as Haumea's shadow swept across the continent, different telescopes would sit at different points along its path. Some would be near the centre of the shadow, catching a long blackout. Some near the edge, catching a shorter one. Some might catch the star just grazing the world's tip. And by combining all those different timings, all those different chords cut across the hidden world. They could reconstruct not just how big Haumea was, but its actual outline, its true egg-shaped profile, traced out in the sky by the pattern of vanishing starlight. A dozen telescopes, a dozen slightly different shadows, stitched together into the sharpest portrait ever made of a world no one has ever visited. And so we return to that winter night, the 21st of January, 2017. The instruments are ready. The skies, in enough places, are clear. The prediction holds. And at the appointed moment, all across Europe, that faint star begins, telescope by telescope, to blink out behind the onrushing shadow of Haumea. The astronomers watch their screens. The light drops. The seconds are counted. The world draws its own silhouette across the sky, and in the data pouring in from all those separate mountaintops, they have exactly what they came for. The truest measure yet of that stretched and spinning egg. 2,320 kilometers long, 1,000 kilometers thick. The egg shape, confirmed at last, not guessed from a flicker, but measured from a shadow. To the kilometer, from 4 billion kilometers away. But that, as it turned out, was not the whole of what the shadow revealed that night. Because when the astronomers looked closely at the timing of the starlight, closer still, at the moments just before the star vanished behind the solid body of Haumea, and just after it emerged, they found something in the light they were not expecting. A small thing, a brief thing, an extra flicker on either side of the main event, where there should have been nothing at all but empty space and steady starlight. 2 little dips, 2 faint winks of the star, before and after the world itself passed by. And those 2 little dips, those unexpected flickers in the dark, were about to rewrite what we thought was possible in this cold and distant corner of the solar system. Because nothing, according to everything we thought we knew, should have been there to block that light at all. But we will come back to those 2 small dips. We will come back to them, and when we do, the story they tell will be extraordinary. For now, though, let the shadow do its quieter work first. Let it give us the shape. Because the shape is where everything about this world begins, and the shape is the thing that, once you understand how it came to be, turns Haumea from a simple oddity into something that feels almost like a natural argument, a physical proof, worked out in ice and rock over billions of years, of the way that spinning things are pulled and stretched by the forces they carry inside themselves. You already know the number, 2,320 kilometers along the long axis, 1,000 along the short. But a number, by itself, is only an address. It tells you where something lives without telling you what it is. To understand what those dimensions mean, why Haumea is that shape and not some other, why no other large body in the solar system has been found in that same stretched and lopsided condition, you have to go back further. You have to go back to before the shadow, before the moons, before the telescopes at Keck, before the discovery announcement in 2005, back to the very first clue that something about this object was genuinely, profoundly strange. That first clue was light. Not the light of a passing star, not the infrared glow of a distant body against a cold sky, but Haumea's own reflected sunlight, faint and flickering, reaching Earth across 4 billion kilometers and falling into the detectors of telescopes like a slow, soft pulse. A pulse that changed. Every 3.9 hours or so, the brightness of Haumea would rise, and then fall, and then rise again, cycling through a variation of roughly 3/10 of a magnitude. For a moment, if you don't work in astronomy, that number might not mean much. So consider it this way. Imagine holding a large, polished egg in the sunlight and turning it slowly in your fingers. When its broadside faces you, you see its full width, its greatest reflecting surface, and it is bright. When it turns so that you are looking at it nearly end-on, you see only the narrow, pointed profile, and it is noticeably dimmer. The reflected light changes, not because the egg itself has changed, but because the shape you are seeing changes as it rotates. That is what Haumea was doing, 4 billion kilometers away, cycling through its long face and its short face, its broad, bright broadside, and its narrower, dimmer end, over and over, every 3.9 hours. It was a team of astronomers, led by David Rabinowitz at Caltech, that put together the picture from those fluctuations in work published in 2006. The light curve they recorded was unmistakable. The variation was large, larger than you would expect from a spherical body with surface patches of different brightness. A sphere can vary in reflected light too, if it has darker and lighter regions rotating past you, but a sphere's light curve has a particular shape, and what Haumea's curve showed was different. It showed something elongated, something turning on its long axis and presenting alternately its wide face and its narrow face to a distant observer. That light curve told the story of an egg, 3 years before any occultation confirmed it to the kilometer, and that same curve, almost in the same breath, told the story of the spin. 3.9 hours, about 235 minutes for a full rotation, which, if you stop to feel it, is almost indecently fast for something so large. The Earth, a body of some 12,000 kilometers across, takes 24 hours to complete one turn. Mars takes a little under 25. Even Jupiter, the great spinning giant, the fastest rotator among the planets, takes just under 10 hours. And Haumea, a world roughly as wide as the United States is long, makes that full circuit in under 4. To put a human frame around it in the time it takes most of us to get through a single workday, Haumea has turned on its axis more than twice. In a week, it completes more than 40 rotations. It does not sit still. It has never sat still. It is, by every measure we have, the fastest spinning large body in the known solar system, and that velocity, that furious self-rotation, is not incidental to its character. It is the source of everything strange about it. Here is the physics. Gently, every spinning body feels 2 competing forces in its own interior. Gravity pulls every part of it inward toward the center, trying to draw it into the most compact possible shape, which is a sphere, and the rotation pushes outward in the way that a carnival ride pushes you against its wall, trying to fling material away from the center. The faster you spin, the harder that outward push. For most bodies, gravity wins easily, and the result is something close to a sphere, or an oblate spheroid, slightly squashed at the poles, slightly bulged at the equator, like Earth, like the Moon, like most of the large worlds we know. But for a body spinning fast enough, the balance tips. The outward centrifugal effect grows strong enough that a sphere is no longer the equilibrium shape. Instead, the body elongates along its rotation axis, pulling out into something more like a rugby ball, or an egg, or an American football. The technical term for this shape is a Jacobi ellipsoid, after the 19th century German mathematician Carl Gustav Jacob Jacobi, who worked out the mathematics of how a self-gravitating fluid body finds its equilibrium under rapid rotation. A Jacobi ellipsoid is what you get when spin has tipped the balance far enough to deform a round world into something you could, without much exaggeration, pick up and throw. Haumea is a Jacobi ellipsoid. a real one, existing out beyond Neptune. Not as a thought experiment, but as a mountain of ice and rock 2,320 kilometers long that arrived at its current shape through the same mathematics Jacobi wrote down in the 1830s. That alignment between an abstract proof worked out by a 19th century mathematician and a frozen world discovered 2 centuries later in the outer solar system has a certain quiet satisfaction to it. The universe follows the equations. It always does. The equations were right about Haumea before Haumea was known. But there is something else the shape tells us, something that makes Haumea even more interesting than just a fast spinner. The Jacobi ellipsoid is a shape that only exists within a certain range of rotation speeds. Spin too slowly, and gravity pulls the body back toward a sphere. Spin too fast, and the centrifugal effect tears the body apart entirely, or flings pieces off the surface, or causes the whole thing to break up into a cloud of fragments orbiting each other. The Jacobi ellipsoid exists in the middle zone, where spin and gravity are in a tense equilibrium, holding the elongated shape together without quite letting it fly apart. And Haumea, spinning once every 3.9 hours, sits very near the fast edge of that zone. Near, but not past. It is as if someone turned a dial, slowly increasing the rotation of this distant world, and stopped it at almost the last possible moment before the world itself came undone. A little faster, and Haumea as we know it might not exist. It might have shed itself into a ring, or scattered its mass into a cloud, or split into pieces that drifted apart. Instead, it sits at the edge, holding, spinning at what feels, from a physical standpoint, like the very limit of what a solid, icy world can endure and remain whole. This is part of why the Jacobi ellipsoid shape matters beyond mere curiosity. It is itself an argument. A body in a Jacobi ellipsoid configuration is a body that has, over time, reached a state of hydrostatic equilibrium, the condition where the material is distributed as if it were a fluid finding its own level under the combined forces of gravity and rotation. Hydrostatic equilibrium is, in fact, one of the defining conditions that the International Astronomical Union uses to classify something as a dwarf planet rather than merely a minor planet or an irregular chunk of debris. It means the body is large enough, massive enough, that its own gravity has shaped it into the equilibrium form, rounded in the general sense of the word. Even if that rounding happens to be the shape of an egg rather than the shape of a ball. And Haumea is massive. Not massive in the way that Jupiter is massive, not massive on a planetary scale, but massive for what it is, for where it lives, for the cold and distant neighborhood it calls home. The figure that comes from the careful analysis of its moon's orbital motions is approximately 4 × 10⁻20 kilograms, written as a number, that is 4 followed by 21 zeros, which is not something a human mind can picture directly. A better frame, it is roughly 1/3 the mass of Pluto. And Pluto itself is not a large world by any standard, so Haumea, in absolute terms, is a small thing. But in its own neighborhood, in the scattered population of the Kuiper Belt, where most objects are small irregular lumps of ice and rock, often only tens or hundreds of kilometers across, Haumea is substantial, massive enough to have pulled itself into that egg shape, massive enough to hold moons, massive enough to have once, long ago, torn itself partially apart and scattered debris across a region of space that still carries the evidence of whatever happened. The mass figure comes not from weighing Haumea directly, of course, because you cannot step onto a scale 4 billion kilometers away. It comes from the same elegant indirect method that astronomers use throughout the solar system. Whenever they want to know how heavy something is, they watch what orbits around it. A moon in a stable orbit carries information about the central body's gravity in its speed, its distance, and the time it takes to complete each circuit. The mathematics connecting these quantities to the central mass is one of the most reliable relationships in all of physics, derived ultimately from Newton's law of gravitation and tested across centuries and across scales, from satellites around Earth to planets around the Sun. For Haumea, the orbital motions of its two moons, its two companions in this cold place, which we will come to properly in a moment, were analysed by Darin Ragozin and Mike Brown, with work published in 2009, to yield that mass estimate of roughly 4 times 10 to the 21st kilograms. The moons became the scales on which Haumea was weighed. And once you have the mass, once you know how heavy the body is, and once the 2017 occultation gave you the dimensions with kilometre precision, you can calculate the density. You divide the mass by the volume, the way you would for a stone dropped into water. And what comes out is a density of somewhere between 1,800 and 2,000 kilograms per cubic metre, depending on how you handle the various uncertainties. To put that in physical terms, pure water ice has a density of about 900 kilograms per cubic metre. Rock, silicate rock, the kind that makes up Earth's mantle, runs somewhere around 2,500 to 3,000. Haumea's density falls in between, higher than pure ice would give you, but lower than you would expect from solid rock all the way through. That number is a fingerprint. A body with a density in that range, with a water-ice surface signal coming in from the spectroscopes and a mass sufficient to force hydrostatic equilibrium, is almost certainly a differentiated body, which means it has layers. A dense rocky core in the centre, where heavier silicate minerals have sunk inward under gravity over billions of years. And surrounding that core, an icy mantle, a thick shell of water ice and possibly other ices, lighter in density, sitting atop the heavier rock below. The same general structure as Earth, in its way, except that where Earth has iron and nickel in its core and silicate rock in its mantle, Haumea has silicate rock in its core and water ice in its mantle. A layered world, an onion, not a uniform block. This layering is not a small detail. It matters for understanding the history of Haumea, for understanding where its moons came from, and why the Kuiper belt around it carries the fingerprints of a long-past catastrophe. But it also matters for understanding the surface itself, which is where the next puzzle waits. And that puzzle is perhaps the most counterintuitive thing about this strange and distant object, stranger in its way than the egg shape, stranger even than the ring that we have not yet arrived at. The surface of Haumea is covered in water ice. Not a dusting of ice, not traces, but a surface reading dominated by crystalline water ice, the same ordered structure as the ice you might find in a glass, or the ice forming on a window on a cold night, or the ice you are walking on when you cross a frozen lake. Crystalline water ice, identified clearly in the near-infrared spectra, the spectral fingerprints measured by Chadwick Trujillo and colleagues in work published in 2007, using the same kind of spectroscopy that tells you what a star's atmosphere is made of or what an asteroid's surface minerals are. When you spread starlight out into its component wavelengths, water ice leaves specific marks. Specific absorption features at specific wavelengths, and Haumea's spectrum shows those marks. The surface is made of water ice. But here is the puzzle. Out in the Kuiper Belt, at 50 AU from the Sun, the environment is extraordinarily hostile to crystalline ice. Not hot, it is not hostile in the way that fire is hostile to ice. Quite the opposite. The problem is radiation. The Sun, even this far out, is still emitting ultraviolet light. Cosmic rays, high-energy particles from galactic sources, are streaming through interstellar space and hitting the surface of every object in the outer solar system. And this radiation, over time, disrupts the orderly crystalline structure of water ice. It jostles the molecules out of their neat rows and lattices, breaking the long-range order, converting crystalline ice into what is called amorphous ice, a disordered, glassy form of the same substance where the molecules have lost their regular arrangement. The process is not instantaneous, but it is relentless. Estimates suggest that, on the timescale of roughly 10 million years, a surface exposed to the radiation environment of the outer solar system should be substantially converted from crystalline to amorphous ice. 10 million years sounds like a long time. And by human standards, it is. The entirety of recorded human history, from the earliest writing to the present, spans perhaps 5,000 years. 10 million years ago, our ancestors were small apes in Africa, not yet walking upright with any reliability. 10 million years is deep time. But in the context of the solar system, which is about 4.5 billion years old, 10 million years is barely a breath, an eye blink, a fleeting moment in the almost incomprehensible span of planetary history. And Haumea is old. Whatever event or events shaped it into its current form happened hundreds of millions of years ago, at minimum, possibly billions of years ago. The moons have been orbiting for that long. The family of fragments that we will explore has been drifting on related orbits for that long. Haumea has been out there, spinning and spinning, for an almost unimaginable stretch of time. If the radiation conversion of crystalline to amorphous ice works on a 10 million year timescale, then over the lifetime of Haumea, the surface should have been converted and reconverted and converted again hundreds of times over. The surface should be amorphous ice. Old, radiation damaged, glassy ice. Not the bright, ordered, crystalline version that the spectroscopes show. And yet, the spectroscopes show crystalline ice. The surface reads as fresh, ordered, bright. The molecules are in their neat lattices. The radiation damage, if it is happening, and it must be happening, because the radiation is real and the physics is real, is somehow being undone. The surface is, by some process that astronomers are still actively debating, staying fresh. How? There are several candidate explanations, and none of them is definitively confirmed. One possibility is that Haumea's interior still contains radioactive elements, potassium, thorium, uranium, the same long-lived radiogenic heat sources that keep Earth's interior warm billions of years after formation, and that this radioactive decay generates enough heat, slowly but continuously, to melt or sublimate and refreeze the surface ice, cycling it back to its crystalline form before the radiation can fully disrupt it. A kind of geological self-renewal, too slow to see on any human timescale, but persistent enough to keep the surface fresh over millions of years. Another possibility involves tidal effects, the gravitational pushing and pulling between Haumea and its moons, which could flex the interior and generate frictional heat in a way that drives some kind of cryovolcanic activity. Ice water or slush periodically welling up and refreezing at the surface, covering the radiation-damaged layer with new crystalline material. And a third possibility, perhaps the most straightforward, is simply that the fast spin itself plays a role. that the spin-related stresses on the surface occasionally crack it or churn it, exposing fresh ice from below. None of these explanations is fully satisfying on its own, and the honest scientific answer is that the crystalline ice on the surface of Haumea is, as of now, genuinely unexplained. It is an open question. The data is clear. The ice is crystalline. The expectation is equally clear. It should not be, not after all this time. Something is keeping it fresh. What that something is remains one of the real unsolved puzzles of Kuiper Belt science, and it is the kind of puzzle that, if you sit with it quietly, has a particular quality to it. The quality of a locked room with no visible door. The surface of Haumea is telling you something about its interior, about its history, about whatever processes are still active out there in the cold and dark, and the message is not yet fully decoded. The freshness of the ice is also part of why Haumea is so bright. Its albedo, a measure of how reflective its surface is estimated somewhere in the range of 50 to 80%, which is to say, between half and 4/5 of the sunlight that hits Haumea's surface is reflected back into space, rather than absorbed. For comparison, fresh snow on Earth reflects about 80 to 90% of sunlight. Clean, new snow, the kind you might see on a mountain the morning after a heavy fall. Haumea's surface has that same quality of reflectiveness. It is a bright world in terms of what it does with sunlight, even though it sits so far out that the sunlight reaching it is already just a faint suggestion of what we receive here on Earth, roughly 1/2500th as intense. 4 billion kilometers away, and still bright enough to reflect back the light. That brightness is the ice, holding its crystalline order somehow, against everything the radiation environment should be doing to it. But the surface is not entirely uniform. Not entirely that same blue-white glitter of fresh, crystalline water ice across every square kilometre of its elongated area. There is a feature, inferred from careful photometric observations, from watching how the overall brightness of Haumea changes as it rotates and comparing the light curve's detailed shape to what a perfectly uniform surface would produce, a feature that astronomers have called the dark red spot. The name is evocative, and deliberately so, carrying an echo of Jupiter's Great Red Spot, the enormous storm system in Jupiter's atmosphere that has been turning for centuries. But Haumea's dark red spot is a different kind of feature, quieter in its science, more tentative in its status. What the photometry shows is that one region of Haumea's surface is measurably darker than the surrounding ice, and measurably redder in colour. Darker meaning it reflects less light, which could indicate a different composition, or a different texture, or a thicker coating of some absorbing material. Redder meaning the reflected light shifts toward longer wavelengths, toward the red end of the visible spectrum, which is a characteristic signature of certain carbon-rich organic compounds, the kind of complex molecules that form when simple ices and organic precursors are hit by radiation over long periods. Astronomers call these compounds tholins, from a Greek word meaning muddy or murky, and they are found on a number of reddish outer solar system objects. From the surface of Pluto, which has reddish regions attributed to tholins formed in its thin nitrogen atmosphere, to many of the small Kuiper Belt objects, whose reddish colours mark them as radiation-processed organics. The analysis of Haumea's light curve that revealed this darker, redder region was carried out by Pedro Lacerda and colleagues, with work published in 2008. Lacerda described the feature as a dark spot, more precisely as a hemispherical feature with a different albedo and colour from the rest of the surface, But it is important to hold this claim at the right level of certainty. The dark red spot is not something that has been seen directly, not something resolved in an image, not a feature visible in a photograph, because there is no photograph of Haumea with the resolution to show surface features. It is inferred from the pattern of brightness variations as the world rotates. It is a deduction from data, not an observation in the most direct sense. And that distinction matters because the detailed interpretation, exactly how large the spot is, exactly what it is made of, exactly how it formed, depends on modelling assumptions that may not be perfectly correct. What does seem clear is that the surface is not perfectly homogeneous. There is something on part of Haumea's surface that is different from the bright, crystalline ice that dominates elsewhere. Whether that something is a tholin-rich patch built up over billions of years of radiation exposure, whether it marks a region of different composition or texture, whether it is connected somehow to an underlying feature in the interior, perhaps a place where the rocky core comes closer to the surface, these are questions without definitive answers. The dark red spot is more of a hypothesis with supporting evidence than a confirmed, well-characterized feature. It is one more layer in the record of a world that keeps offering you partial answers and new questions in the same breath. And there is something fitting about that. Fitting for a world this far away, this small, this difficult to see clearly from any distance. Haumea has been teaching from the very beginning a kind of astronomy that requires you to sit with partial information and build a picture from inference. The light curve gave you the spin and the elongation before you had the dimensions. The dimensions came from a shadow, not a photograph. The mass came from moons whose orbits you calculated, not from any device you sent to orbit Haumea itself. The surface composition came from spectral fingerprints in infrared light, not from a sample anyone collected. The dark red spot came from a subtle variation in a brightness record. Everything is indirect. Everything is deduced. And yet the picture that emerges from all those indirect lines of evidence is richer than you might expect from a world no spacecraft has ever approached. Richer and stranger, and more specific than a world that, in some sense, we have only ever glimpsed through the behaviour of light. That is the method. And as you lie here, as the darkness settles and the quiet deepens, that is perhaps the thing worth carrying into sleep, that the universe is not only knowable through proximity. You do not always have to go somewhere to understand it. Sometimes the light that comes back to you carries more than you thought. A flicker of brightness, rising and falling every 3.9 hours, carries the shape of an egg. The timing of a shadow carries dimensions measured to the kilometre. An orbital dance of two small moons carries the weight of the world they circle. A subtle redness in a photometric curve carries the suggestion of ancient chemistry, of organic compounds built up slowly over an almost incomprehensible span of time by the patient work of cosmic radiation on simple ices. The surface of Haumea is cold beyond almost anything in ordinary experience. 50 Kelvin, which is minus 223 degrees Celsius. A cold that would make liquid nitrogen seem warm. A cold at which most gases become solids, at which most solids become rigid and brittle beyond any practical use. The surface of Haumea is so cold that water ice is not just present there, it is the dominant solid, the bedrock, the landscape. You would not walk on it the way you walk on ice here on Earth, not with any sense of familiarity. The ice at 50 Kelvin is not the ice of winter ponds or skating rinks. It is harder, denser, more like rock in its mechanical behaviour. The world beneath the ice, the silicate rock of the differentiated core, is buried under kilometers of this substance, insulated by it, held in a darkness and stillness that has not been disturbed by any instrument, any probe, any human-made thing. And above the surface, nothing, or as close to nothing as makes no practical difference. The 2017 occultation, that extraordinarily precise measurement, was also used to probe for an atmosphere. When a body has a significant atmosphere, the starlight does not simply switch off and switch back on cleanly as the body passes in front of it. Instead, the light dims gradually at the edges, refracted through the gas layer, softened by it. The sharpness or softness of those transitions in the occultation light curve carries information about how much gas, if any, is present. For Haumea, the transitions were sharp. Precise, the light cut off cleanly and returned cleanly, with no gradual atmospheric softening at all. The upper limit that Ortiz and colleagues placed on any atmosphere Haumea might have is extremely low. No global atmosphere, no significant gas envelope. The surface is bare, exposed directly to space, sitting under the faint radiation of a sun nearly 50 times further away than it is from Earth, with no air to carry sound, no weather to change the landscape, no wind to move the ice. It is, in some important sense, a world that has been sitting still in that cold and airless condition for a very long time. The spin has not stopped. The spin has never stopped, as far as anyone can determine. Haumea has been turning at this extraordinary rate for hundreds of millions or billions of years, and in all that time the surface has been facing space directly, receiving the cosmic radiation, cycling through that bright long face and that narrower short face, rising and dimming in the light curves of any telescope advanced enough to notice. Until 2005, no one had noticed enough to know those moons were there. Until 2006, no one had published the full picture of the spin and the elongation from the light curve. Until 2007, the spectroscopic signature of the crystalline water ice had not been laid out in full detail. Until 2008, the suggestion of the dark red spot had not been worked out from the photometry. And until 2017, no one had measured the true size to the kilometre. And no one at all had found what was hiding in those 2 extra flickers in the starlight. There is a kind of archaeology in this, not the archaeology of digging through layers of soil for pottery and bones, but an archaeology of knowledge in which each new technique, each new telescope, each new occultation opportunity peels back another layer and reveals something that was always there but invisible until the moment the right instrument arrived and the right method was applied. Haumea did not change between 2006 and 2017. It was always egg-shaped, always crystalline and icy, always carrying whatever is in the dark and rocky core, always spinning. What changed was our ability to read it. That is the shape, then, and the interior and the surface, built up from a decade of accumulating inference. The egg that physics demands a fast, spinning fluid body must take. The differentiated interior that the density calculation requires. The crystalline ice that spectroscopy confirms and radiation physics insists should not still be there. The faint suggestion of a darker, redder region where ancient chemistry may have built something more complex from simple beginnings. A world reconstructed not from photographs, but from flickers and shadows and spectral lines and orbital periods, assembled patiently into something that, if you hold all the pieces together, starts to feel surprisingly real. And out around it, orbiting in slow loops through the same cold dark, there are companions. Small ones, discovered not long after the world itself was found. and carrying their own stories about what Haumea's past might have looked like before it settled into the egg-shaped, solitary, furiously spinning thing it is today. Two moons, two small frozen worlds, circling a larger frozen world, named for the daughters of a goddess, discovered by telescopes aimed at a piece of sky nobody had looked at carefully enough before. They are waiting in the dark out there, and their orbits are not the calm, circular, undisturbed paths you might expect from a world that has been sitting quietly in the outer solar system for billions of years. Their orbits carry their own evidence of violence, their own record of something dramatic in Haumea's deep past. And once you look at those paths carefully, once you understand what an excited, non-circular, mutually inclined pair of orbits implies about the history of the system that produced them, you begin to understand that Haumea did not arrive at its present state quietly. Something happened. Something enormous and violent and irreversible, in a time so distant that the solar system was still young and the outer dark was crowded with debris that has long since cleared away. And the two moons circling out there in the cold are not incidental details, they are witnesses. They are, in a very real sense, survivors of whatever that event was, carrying the record of it in the shape and tilt and eccentricity of every orbit they trace. Let's begin with Hi'iaka, the outer moon, the larger of the two. She was discovered in 2005, less than a year after Haumea itself first appeared as a moving point of light in archived telescope images, and her discovery came the same way everything about this system comes, through careful, patient observation with instruments pointed at a very specific patch of distant sky. The team that found her was led by Mike Brown at the California Institute of Technology, working with the Keck Observatory high on the summit of Mauna Kea in Hawaii, where the air is thin and the sky is dark, and the mirrors are large enough to pull in light from objects so faint they are essentially invisible to any telescope smaller or less precisely aimed. Brown's team had been surveying the outer solar system, cataloguing distant bodies, and when they turned their attention to the object that would become Haumea, they found not just the central world, but, orbiting around it, a companion. Then a second companion. Two small frozen things, circling a larger frozen thing. All of them so far from the sun that the light reaching them had already made the journey to Earth and back several times over in the time it had travelled to reach them. Hi'iaka is roughly 300 to 400 kilometers across. That is a wide range, and the uncertainty tells you something about how difficult these measurements are when the object in question is a dim, unresolved point of light, even in the most powerful telescopes we have. But somewhere in that range, 300 to 400 kilometers, sits a world. It is tiny by planetary standards. It is smaller than many asteroids, smaller than most things we might casually call significant. And yet it is a world with its own gravity, its own surface, its own composition. And the composition is familiar: water ice. Spectroscopy, the same technique that revealed Haumea's crystalline surface, has detected water ice on Hi'iaka as well. The same bright, clean, reflective material that makes Haumea gleam despite the darkness and the distance. She carries a piece of her parent body's identity in her very surface. Her orbit around Haumea takes approximately 49 days to complete. 49 days to trace one loop around the central world, a slow and distant path that keeps her well out from the surface. The radius of that orbit, the distance between the two bodies as she circles, is large enough that you could fit several Earths end to end in the gap between them and still have room. She is the outer moon, the more distant companion, and her orbit is, compared to her siblings, relatively well behaved. Not perfectly circular, not perfectly aligned with any tidy reference plane. But compared to Namaka, the inner moon, Hyaka's path has a kind of order to it that allows astronomers to track her reliably, to follow her around the sky, to measure the arc of her passage, and from that arc extract the gravitational information that tells us how massive the system is. Namaka is different. Namaka is the inner moon, smaller than Hyaka, rougher in her behavior, harder to track. She is perhaps 150 to 200 kilometers across, again, a range, because the uncertainty grows larger the smaller and fainter the object, and she completes one orbit around Haumea in approximately 18 days. 18 days to trace her loop, a shorter, faster path, because she is closer in, pulled around more sharply by Haumea's gravity. But the shape of that path is not the smooth circular arc you might draw with a compass on a piece of paper. It is stretched, it is tilted. It is what orbital mechanics describes as eccentric and inclined, meaning that her distance from Haumea varies over the course of each orbit, and her orbital plane does not match the equatorial plane of Haumea itself or the orbital plane of her sibling Hyaka. She moves through a slightly different slice of space, tracing a path that is pulled at an angle to everything around it, wobbling and varying in a way that a moon in a calm, undisturbed system simply would not do. The two orbits interact with each other gravitationally. They tug at each other, the two moons, pulling in subtle ways that compound over time, shifting the shapes of both paths in slow oscillations that span years and decades. This mutual gravitational conversation is itself a source of information. By watching how the orbits evolve, astronomers can work backward, constructing models of the orbital history of the system, testing scenarios for how the moons might have ended up where they are. And what those models tell you, consistently, is that the system has been through something. The orbits are not the quiet, settled paths of moons that formed gently in a calm disk around a calm central body. They carry the signature of a system that was disrupted, that was shaken, that was produced by some process that left the participants still ringing with the energy of whatever happened to them. The names themselves carry their own quiet significance. Hyaka and Namaka are the daughters of Haumea in Hawaiian tradition. Haumea is a goddess of childbirth and fertility, and she is the mother of many children. In the stories, she gives birth to the islands of Hawaii. She is the source of abundance, the origin of things that grow and multiply. Naming the central world after her and the moons after her daughters is not just poetic decoration. It is an acknowledgement of something real in the physical structure of the system. The moons almost certainly came from Haumea herself, born in some sense from a catastrophic event that tore material away from the larger body and sent it orbiting. The name chosen for the outer moon, Hyaka, belongs to a goddess who is the patron of the island of Hawaii itself, associated with hula, with creative expression, with the island's deepest cultural traditions. The inner moon, Namaka, takes the name of a water spirit connected to the ocean, to the restless and unpredictable movement of water. There is something fitting in that. Namaka's orbit is restless. It does not sit still. It moves in ways that keep changing, that require constant observation to track, that refuse to settle into anything clean and predictable. Now, the moons are not alone in the outer solar system as evidence of Haumea's violent past. They are, in a sense, the closest and most obvious survivors. But spread across a much larger region of the Kuiper Belt, moving along orbits that are related to Haumea's in ways that are not coincidental. There is a scattered population of smaller objects that share a distinctive and striking characteristic. A characteristic that, when astronomers first recognized it, was essentially unprecedented in the outer solar system. These objects are covered in water ice, not the common, dirty, dark, reddish-tinged surfaces that most Kuiper Belt objects wear. Most outer solar system bodies have been darkened by billions of years of radiation and chemical processing, their surfaces stained with complex organic compounds called tholins, substances built up over immense time when radiation breaks apart simple molecules and reassembles them into something more complicated and darker. That process, over the deep timescale of the solar system, tends to produce surfaces that are red or brown or nearly black, absorbing light, reflecting little. The standard outer solar system surface color is not white, it is dark. And yet here, scattered across a region of the Kuiper Belt, is a cluster of objects whose surfaces are not dark. They are bright. They reflect light. They show the spectral signature of water ice, clean and unmistakable. The connection to Haumea was recognized in 2007 in a paper published in the journal Nature and led by Mike Brown, the same person who had already discovered Haumea and its moons. The argument was straightforward, and the evidence for it was compelling enough that the scientific community accepted it fairly quickly as a genuine discovery. What Brown and his colleagues identified was the first collisional family ever confirmed in the Kuiper Belt. A collisional family, in the language of planetary science, is a group of objects that share a common origin. They are the fragments of a larger body, or the debris scattered from a collision between bodies, and they carry the memory of that shared origin in the similarity of their orbits and their compositions. Collisional families were already well known in the asteroid belt, the broad ring of rocky bodies between Mars and Jupiter, where large populations of small bodies have been crashing into each other for billions of years and leaving families of related fragments behind. But the Kuiper Belt, despite being populated by many thousands of objects, had not been shown to host any families. The Haumea family was the first, and it remains, to this day, the only confirmed one. The family members that were identified in Brown's 2007 analysis included several objects that had already been catalogued and given provisional designations, the alphanumeric labels that newly discovered solar system objects receive before a formal name is assigned. Objects like 2002 TX300, a body several hundred kilometers across, with a surface that gleams with the same clean water ice signature as Haumea itself. Objects like 1995 SM55 and 1996 TO66 and others in that scattered population, each carrying its own provisional label, each occupying an orbit that, when analyzed carefully, shows the hallmarks of kinship with Haumea, a similar tilt, a similar range of distances from the Sun, a trajectory through space that is consistent with having been launched from a common source at some point in the distant past. Not all candidates are equally certain. Membership lists in collisional families are always somewhat provisional because identifying a true family member requires distinguishing between objects that really do share a common origin and objects that simply happen to be in nearby orbits by coincidence. But the core of the family, the subset with both the orbital clustering and the matching spectral signature, is well established, and it represents something real about the history of the outer solar system. What the spectral signature means, concretely, is this. When you spread the light reflected from one of these objects out into its constituent wavelengths, which is what a spectrograph does, the instrument that turns a point of light into a rainbow of information. You see particular wavelengths absorbed more strongly than others, and the pattern of those absorptions is specific to particular materials. Water ice absorbs infrared light in characteristic ways. Carbon-rich compounds absorb different wavelengths. Rocky silicates leave their own signature. The spectra of Haumea family members consistently show the signature of water ice, and the absence of the dark organic overprinting that would develop over billions of years of unprotected exposure to radiation. Which means the surfaces are, in cosmic terms, young, not necessarily freshly formed, but freshly exposed. Material that was buried inside a larger body, shielded from the radiation that darkens outer surfaces, and then brought to the surface by an event that shattered or stripped the exterior layers away, exposing the clean ice beneath. That is what an ancient collision would do. If a large body in the early Kuiper belt, a body even bigger than Haumea is today, were struck by a significant impactor or were otherwise disrupted, the interior material, the clean ice, the stuff that had never been exposed to space, would suddenly be scattered outward, travelling away from the impact site on trajectories determined by the geometry and energy of the collision, spreading into a population of smaller bodies, each carrying a surface of pristine water ice. The energy of the event would also do something else. It would change the rotation of the surviving central body. If the collision or disruption imparted angular momentum to Haumea, if it set the remnant spinning faster, then that increased spin rate would drive the shape change that the light curves have so clearly revealed. The spin-up and the scattering of icy fragments are, in this framework, two consequences of the same catastrophic event. The timeline for this event, in the leading version of the story, is ancient. Not just old in the way that human history is old, or even in the way that the dinosaurs are old. Ancient in the way that the solar system itself is ancient. The collision is commonly placed more than 1 billion years ago, and some estimates push it back further still, toward the first 1 billion years of solar system history, when the outer solar system was more crowded and chaotic, when giant planets were still migrating and their gravitational influence was reshaping the architecture of the Kuiper belt and scattering debris in ways that made large collisions more likely. The exact timing is uncertain. The kind of forensic analysis that would pin down the age of an event in the outer solar system to better than hundreds of millions of years is simply not available from the data we have. But old. Very, very old. The fragments that are now spread across the Kuiper belt have been travelling on their independent orbits for a span of time that is difficult to hold in the mind without some kind of grounding analogy. Consider that 1 billion years ago, the most complex life on Earth was still unicellular. There were no plants, no animals, no fungi in the modern sense. The continents were arranged in configurations we would not recognize. The shallow seas were full of microbial mats, and the atmosphere was still transforming, and the world was unimaginably different from anything we have ever experienced or could experience. That is roughly how long the Haumea family members have been traveling their separate paths through the outer solar system. Each fragment launched outward from a single catastrophic moment, then moving, silently, slowly, alone, for all of the time that passed between then and the night in 2007, when a spectrograph on a telescope in Hawaii identified the family and told the story of their shared origin. There is something worth sitting with in that image. Billions of years of silent travel. Billions of years of frozen, solitary motion through a darkness where the sun is merely the brightest star, not the warm presence it is from here. The family members have been companions in a very loose sense, sharing a region of space, sharing an orbital kinship, sharing the same faint signature of water ice that marks them as siblings. But they have never been close together since the moment of their separation. They dispersed. They went their own ways, and they have been going their own ways, in the outer dark, ever since. The moons, Hiyaka and Namaka, are thought to be part of the same event, not scattered into distant independent orbits like the family members, but captured or reaccreted, pulled back together by gravity, into orbits around the surviving central body. The exact mechanism by which a collision or disruption produces bound satellites rather than freely escaping fragments depends on the geometry and energy of the event, and it is not trivially easy to arrange. Debris from a collision tends to fly outward, not settle into neat orbits. Something about the specific conditions of what happened to Haumea produced two companions that stayed, while other debris escaped into the broader Kuiper belt. The details of how that happened are part of what makes the origin question not yet fully answered. And here is where the honest version of the story requires a pause and a kind of admission. Because the narrative that has been built around Haumea's origin, the tidy, satisfying account of a single giant impact that spun up the central body, scattered the moons, and seeded the Kuiper belt with icy family members, is a compelling story. It has a clarity and an elegance to it that is appealing. Everything explains everything else. The fast spin, the egg shape, the two moons, the scattered family, all arising from one ancient catastrophic moment. It is the kind of unified explanation that science loves, and that works rhetorically as a narrative, and that appears in most popular accounts of Haumea as though it were settled fact. But it is not settled fact. It is the leading hypothesis. And there are scientists who have looked carefully at the details of what the giant impact scenario actually predicts and compared those predictions to what is actually observed, and found that the fit is not as clean as the story implies. The specific problem involves what is called the velocity dispersion of the family members. When fragments are ejected from a collision, they carry the energy of that collision in their relative velocities, how fast they are moving relative to each other after the event. The geometry of the collision determines these velocities, and the total energy of the collision constrains how spread out the fragments can be. The Haumea family members, when you examine their orbits carefully and work backward to estimate how fast they must have been moving relative to each other when they separated, turn out to be moving surprisingly slowly relative to one another. Their velocity dispersion is very small, tighter than you would expect from a large impactor hitting Haumea hard enough to spin it up to its current rotation rate and scatter all the debris we see. A harder, more energetic collision would spin things up more, yes, but it would also scatter the fragments more widely, faster, into a more dispersed family. The observed family is too compact, moving too slowly. For the most straightforward version of the giant impact story to reproduce cleanly. This tension has led to alternative models. One class of alternatives proposes that the event was not a head-on or high-energy impact between Haumea and a separate impactor, but something different, perhaps the disruption of a large satellite that was already orbiting Haumea. In this scenario, Haumea begins with a significant moon, not a small one, but a large one, perhaps comparable in size to the moons of some of the larger Kuiper belt objects. That large satellite, over time, through tidal interactions with Haumea or through a collision of its own, becomes disrupted. Its material escapes, and as it does, it carries angular momentum that transfers to Haumea itself, spinning up the central body to its current rapid rotation. The scattered debris from the disrupted satellite becomes the family members. The moons we see now, Hiyaka and Namaka, are the surviving remnants, or new objects formed from some of the debris that was reaccreted. Another alternative involves what planetary scientists call a graze and merge event. Rather than a clean impact by a separate object, two similar-sized bodies collide at a glancing angle and then merge, a slow, partially inelastic collision that deposits angular momentum into the surviving merged body without the high relative velocities that a more energetic impact would produce. The resulting body rotates rapidly because the collision was glancing and transferred its spin. But the ejector velocities are lower because the collision energy was not as high. This could, in principle, produce a collisional family with the right velocity dispersion while also explaining the rapid rotation and the egg shape. These alternatives are not the consensus. The giant impact story remains the most widely discussed framework, and the family's existence is not in question. The family is real, confirmed. The orbital and spectral evidence for it is solid. What is debated is the exact nature of the violence that produced it. A single clean impactor, a disrupted satellite, a glancing merger, these are not small distinctions, but they are distinctions that the available data has not yet been able to settle decisively. The observations that would cleanly distinguish between them require either much more detailed orbital analysis, particularly of Namaka's complex path and its interaction with Hiyaka, or a close-up view of the whole system from something that has actually travelled out there. And nothing has travelled out there. No spacecraft has ever been within any useful distance of Haumea. Everything we know has come from here, from Earth-based and near-Earth telescopes, from the light that Haumea and its companions choose or are forced by circumstance to send our way. Which means the origin story of the Haumea system is, in an honest sense, still open. The chapter is not finished. The evidence points strongly towards some ancient catastrophic event. The family is real, the moons are real, the excited orbits are real, the crystalline surface is real, and all of these things together tell you that something dramatic happened. But exactly what, and exactly when, and exactly how, the mechanism of the violence, the precise geometry of whatever torn apart and scattered moment produced this system, remains a question that careful scientists still argue over in the published literature, in conference rooms, in the careful language of papers that present modelling results and then acknowledge, in sections titled Discussion or Caveats, that the model does not yet perfectly match the observations and that alternative scenarios cannot yet be ruled out. This is worth naming not to undermine the story, but because the uncertainty is itself part of the story. The honest picture of Haumea is not a closed book. It is a case file that keeps getting richer, that keeps receiving new evidence. That keeps prompting new interpretations. The family was discovered in 2007. The moons were discovered in 2005. Haumea itself was identified in 2004. That is remarkably recent. We have been seriously examining this system for barely 2 decades, and in those 2 decades the picture has already changed substantially. The size estimates have been revised. The density has been recalculated. The ring has been discovered, the family's origin has been contested and debated. The thing that was true in 2006 is not quite what is believed in 2017 and beyond. The file is active. Namaka's orbit, in particular, remains a continuing source of information and uncertainty. Because her path is eccentric and inclined and gravitationally entangled with Hyakkus. The evolution of her orbit over time is sensitive to the exact parameters of the whole system, the masses of both moons, the oblateness of Haumea, the long-term gravitational effects of distant objects. Watching Namaka over time, tracking her precise position in the sky over years and decades, can in principle refine the model of the system enough to test the different origin scenarios against each other. Astronomers have been doing this patiently with whatever telescope time they can secure, adding data points to a picture that requires years of observations to assemble. It is slow work. It is the kind of science that does not produce dramatic announcements every few months, but that gradually sharpens the image until something that was blurry becomes clear enough to decide between competing explanations. Out there, right now, Hyakka is completing another orbit. Her 49-day loop, traced at a distance of roughly 50 times the Earth-Sun distance from the Sun, carries her around Haumea at a pace that is glacially slow by inner solar system standards. The sunlight reaching her is about 2,500 times fainter than what Earth receives, barely enough to cast a shadow, barely enough to see by. Her surface of clean water ice, which does reflect that faint light with surprising efficiency, sits at a temperature around 50 degrees above absolute zero, which means roughly minus 223 degrees Celsius. That is not a temperature that allows for chemistry, for change, for the kind of processes that reshape surfaces over geological time. It is a temperature at which things essentially freeze in place, preserving whatever state they arrived in with only the slowest of modifications from incoming radiation over billions of years. Namaka, closer in, traces her shorter loop in 18 days, wobbling in her inclined, eccentric path, tugged gently but persistently by her sister's gravity. The two moons never come close to each other. Haumea's system is not crowded in that sense, but they are close enough and massive enough relative to each other that their gravitational conversation never falls silent. It is a quiet conversation, measured not in voices, but in infinitesimally small accelerations, in the barely perceptible bending of orbital paths that accumulates over decades into something measurable. Astronomers have been listening to that conversation since 2005, and they are still transcribing it, still turning the raw position measurements into orbital parameters, still using those parameters to test what the history of the system must have looked like. The family members, spread across a wider volume of space, travel in their own separate solitudes. 2002 TX300, several hundred kilometers of bright icy rock, moving on its orbit with no awareness of its kinship with the others, carrying its water ice surface through the same cold dark that all of them inhabit. 1995 SM55, 1996 TO66, and the others, each one a separate world, or nearly a world, each one a remnant of whatever moment of violence produced the whole collection. They have been separate for so long that they are no longer a family in any functional sense. They do not interact. They do not affect each other's paths in any meaningful way. The only thing connecting them is the orbital pattern that ties them to a common origin and the spectral signature of ice that tells the story of what they are made of and, through that, where they came from. When you step back and look at the whole system, Haumea spinning furiously in the center, egg-shaped and crystalline, with its rocky core and its icy mantle and its faint dark spot and its complete absence of atmosphere, Hyakka orbiting out at 49 days, small and icy and relatively well-behaved, Namaka orbiting closer in at 18 days, tilted and eccentric and dynamically restless. And then the broader family spread across the Kuiper belt, those silent, icy travelers on related orbits, carrying their shared spectral signature as the only evidence of the ancient moment that connected them. When you hold all of that together, what you are looking at is an entire catastrophe preserved in orbital mechanics. The violence itself happened long ago, in a time before anything on Earth had yet learned to be complex. But the shapes of the orbits, the compositions of the surfaces, the excited paths of the moons, the spreading fan of family members through the belt, these things are the fossil record of that violence, still readable, still carrying their information, still available to be decoded by careful observers with the right instruments and the patience to watch and measure over time. That patience is perhaps the most striking thing about all of this. Not the violence of the ancient collision, not the strangeness of the egg shape, not the mystery of the crystalline ice. Those are all remarkable, and they will be with us for the rest of this story. But the patience, the long, unhurried, telescope by telescope assembly of a picture of a world that no one has ever visited and that no one alive today is likely to visit, the 2005 discovery of the moons, the 2007 identification of the family, the slow accumulation of orbital data that is still ongoing decades later. The willingness to work with what the universe offers, a moving point of light, a spectral signature, an orbital path, and from those slender threads to construct something that resembles understanding. Namaka has not finished telling her story. Hiyaka has not. The family members, with their shared ice and their scattered orbits, carry information that has not yet been fully extracted. And somewhere in Haumea itself, in the exact oblateness of its shape and the precise spin rate and the unresolved question of what keeps its surface crystalline, there are answers to questions that have not yet been fully formulated. The file stays open. The observations continue. And out in the cold, the system spins and orbits and persists, waiting with the infinite patience of frozen things in the dark, for the next instrument to turn its attention that way and find another thread to pull. But there is one more discovery still to come in the story of Haumea. One finding that arrived more recently than the moons, more recently than the family, and that changed in a single night in January of 2017 the entire category of object we thought Haumea was. A discovery that nobody had predicted, that nobody was specifically looking for, that appeared as an extra dip in a graph of starlight and announced itself to a dozen telescopes simultaneously across the face of Europe. A discovery that moved Haumea from the category of strange but comprehensible into something that required a fundamental revision of the kinds of environments where rings can exist. An extra wrinkle around an already extraordinary world. And that wrinkle is a ring. Let that settle for a moment. A ring. The same kind of structure that makes Saturn so immediately recognizable, so breathtaking in every image ever taken of it, that structure of orbiting particles and rubble and dust arranged in a flat plane around a central body, that structure exists, in miniature, around a world so distant that the most powerful telescopes on Earth cannot resolve its shape, can barely pin down its brightness, and had never once, in all the years of watching, hinted that anything circled it beyond its two small moons. A ring, found not by a spacecraft, not by a dedicated search, but by accident in the extra flicker of a distant star on a single January night, caught by a network of observatories that had gathered not to look for a ring, but simply to watch a shadow cross the sky. The story of how that ring was found is in miniature the entire story of how we know anything about Haumea at all. So it is worth telling slowly, A stellar occultation is a kind of astronomical fortune. At some predictable point, a moving body in the solar system will pass in front of a background star as seen from Earth. The star doesn't move, at least not on the timescale of human observation. The body does. And when the body's shadow sweeps across Earth's surface, anyone standing inside that shadow watches the star blink out for some period of time, a few seconds, a few minutes, depending on the body's size and how fast it is moving, and then blink back on. The star isn't gone, of course. It hasn't changed. Something has simply passed between it and you. The way your hand passing in front of a candle makes the candle seem to vanish for a moment. The candle is still there. The hand moved. What makes stellar occultations valuable is the precision they offer. The timing of that blink, measured to fractions of a second from different locations, allows astronomers to reconstruct the body's exact size and shape. Think of it as a silhouette portrait. You can't photograph someone's face from 2 miles away in bad lighting. But if you ask them to walk across a lit doorway and you measure the width of their shadow to the millimeter from 10 different positions, you can reconstruct the width of their shoulders and the height of their head with an accuracy that any photograph would struggle to match. The occultation technique works on the same principle. Multiple sites, each recording the exact moment the star disappeared and reappeared, give you multiple chords through the body's shadow. String those chords together and you have an outline. A true kilometer-precise outline of something too small and too far away to see directly. This was the sharpest tool available. Not the only tool. The light curve photometry had told astronomers about the spin and the elongation, the infrared spectroscopy had told them about the ice, the moon orbits had told them about the mass, but for size and shape, the occultation was definitive. And in 2017, a particularly good occultation was coming. Haumea was going to cross in front of a star-designated URAT-1 533 182 543. And the event was predictable far enough in advance that a coordinated campaign could be organized. 12 observatories across Europe were set up and ready. The night of January 21st, 2017 arrived. The telescopes opened their eyes, and they watched. The star blinked out. That was expected. What nobody was specifically looking for, what nobody had specifically predicted, was what happened just before the main body of Haumea occulted the star, and just after it reappeared. In the data from multiple observatories, there were 2 brief additional dips in the starlight. Not the main blink, which lasted the expected few seconds and corresponded to the solid body of Haumea itself. These were shorter, dimmer, shallower events on either side. The star faded slightly, recovered, vanished completely as Haumea passed in front, reappeared, then faded slightly again, before returning to full brightness. 2 extra dips, one on each side of the main occultation, symmetrically placed. Jos Luis Ortiz and his colleagues at the Sierra Nevada Observatory in Spain, who led the campaign, recognized immediately what they were looking at. Or rather, they recognized the only thing that could plausibly explain 2 symmetrical dips flanking the central body. A ring. Something encircling Haumea in its equatorial plane, something diffuse and thin, blocking enough starlight to register in the data but not enough to be visible in any direct image, and arranged at a distance from the center that placed it in a precise location, roughly 2,287 kilometers from the center of Haumea, in a band about 70 kilometers wide. 70 kilometers wide. That is less than the distance from one end of a mid-sized city to the other. As a fraction of the scale of the solar system, 70 kilometers is essentially nothing. And yet it was there, written in the data, unmistakable once you knew what you were looking at. The team checked the observations from multiple sites. The extra dips appeared in the records from station after station. The geometry was consistent. The conclusion was not dismissible. Haumea had a ring. The paper was published in Nature in 2017, authored by Ortiz and a long list of collaborators, and it announced something the field had not expected to find. It was the first ring ever discovered around a trans-Neptunian object, the first ring ever found around a dwarf planet. And to understand why that was genuinely surprising, why the editors of Nature didn't shrug at the result, it helps to think about where rings had been found before. For most of modern astronomy, rings were a feature of the giant planets. Jupiter has them, thin and faint, discovered by the Voyager 1 spacecraft in 1979. Saturn has the ones you know, the vast, bright, structured disk that makes Saturn the most visually recognizable planet in the solar system. Uranus has them, discovered in 1977 by another stellar occultation. You can trace the technique's pedigree from that discovery all the way to the 2017 Haumea result. Neptune has them, confirmed by Voyager 2 in 1989. 4 giant planets, each with a ring system and no rings anywhere else. The prevailing assumption, never quite stated as a rule, because science is cautious about rules it hasn't tested, was that rings required the gravitational environment of something massive, something large enough to generate the tidal forces that prevent ring particles from coalescing into a moon, something with the size and complexity to maintain a ring over time. Then, in 2013, a small body called Chaotically changed the picture slightly. Chaotically is a centaur, a class of object that orbits between Jupiter and Neptune in the region between the rocky inner solar system and the icy outer one. Chaotically is only about 302 kilometers in diameter, far smaller than any of the giant planets, and it was found, also by stellar occultation, to have 2 narrow rings. The discovery was unexpected. It pushed the environment where rings could exist inward, from the giant planets to the Centaur region. It raised questions about whether rings might be more common than anyone had assumed. But Chaotically was still in a regime closer to the Sun than the deep outer solar system. It was not a dwarf planet. It was not a trans-Neptunian object in the Kuiper belt. And nobody had specifically predicted that Haumea, 5 times farther from the Sun than Chaoticlie's orbit, smaller than Pluto and far stranger in shape, would also have one. The Chaoticlie discovery had opened a door. The Haumea discovery pushed through it and found a much larger room on the other side. What keeps the ring where it is? This is where the geometry becomes elegant in the way that the best physical explanations tend to be, not contrived, not forced, but the natural consequence of forces that were always operating and simply hadn't been observed yet. The ring particles at 2,287 kilometers sit in a specific relationship to Haumea's rotation. They orbit the body once for every 3 rotations of Haumea itself, 1 trip around for every 3 spins beneath them. In the language of orbital mechanics, this is a 3.1 resonance, and resonances, those rhythmic coincidences of orbital timekeeping, tend to be places where things get pinned, where the gravitational conversation between a body and the material around it settles into a stable, repeating pattern. The 3.1 resonance is one of the gravitational landmarks around Haumea, a place where ring material can sit without quickly being herded somewhere else. And that location also happens to be inside, or very near, what is called the Roche limit. The Roche limit is the distance from a body inside which tidal forces. The difference in gravitational pull between the near side and the far side of a small object becomes stronger than the object's own self-gravity. Inside the Roche limit, a loosely bound rubble pile cannot hold itself together. Tidal forces tear it apart. That is why Saturn's rings exist where they do, inside Saturn's Roche limit. Material cannot coalesce into a moon and instead remains dispersed as a ring. The same principle applies, scaled down, to Haumea. The ring at 2,287 kilometers sits in a zone where tidal forces prevent the particles from clumping together, where the ring material is, in a sense, gravitationally forbidden from becoming a moon. It is not that the ring is trapped there arbitrarily. It is that the ring is there, because that is one of the very few places around Haumea where a ring can persist. Take a moment with that. The ring sits where it does because of physics, because of the ratio between Haumea's spin rate and the Keplerian orbital period at that radius, because of the tidal environment near a rapidly spinning elongated body. Everything is connected. The spin that stretches Haumea into its egg shape is the same spin whose rate sets the resonance structure, including the resonance where the ring lives. The shape is not separate from the ring, and the ring is not separate from the spin. All of it comes back to that 3.9-hour rotation, that single foundational fact that cascades through every other remarkable thing about this world. The egg shape, the resonances, the tidal environment, and now the ring. There is something that the 2017 occultation also definitively ruled out, and it is worth mentioning because it closes a loop that had been quietly open since the first observations of Haumea's spectrum. In the data from the shadow crossing, there was no thickening of the star's edges that would indicate a substantial atmosphere. The star blinked out sharply and returned sharply, not gradually, not through the slow fade that an atmospheric layer causes by refracting light around the edge of a body. Whatever gases might have been expected, water vapor, nitrogen, methane, the thin atmospheres that seasonal warming and cooling can produce on other Kuiper Belt objects, were not present at any detectable level. The 2017 occultation set a hard upper limit. Haumea, at 50 times the Earth-Sun distance, with surface temperatures around 50 Kelvin, approximately negative 223 degrees Celsius, is airless, not thinly aired. Airless, the ring orbits a world that has no weather, no sky, no envelope of gas to scatter the sun's pale distant light. Just rock and ice, and the ring itself, and the two small moons moving through the perfect silence of deep space. So there it is, the full inventory, assembled piece by piece across decades of observation from many telescopes and teams. A world that spins once every 3.9 hours, stretched by that spin into a shape roughly 2,320 kilometers long and only about 1,000 kilometers thick at its poles, covered in crystalline water ice that keeps refreshing itself in ways we don't fully understand. Bearing a darker redder patch on one hemisphere that may be enriched with minerals or organic compounds, accompanied by two moons named for the daughters of a Hawaiian goddess, trailing a family of icy shards across shared orbits in the Kuiper Belt, and encircled by a narrow ring of particles at a radius of 2,287 kilometers, 70 kilometers wide, in 3:1 resonance with the world's own spin. Sitting inside the Roche limit where moons cannot form and rings can persist. All of it assembled from light, from shadows, from the timing of a star's disappearance and return. No spacecraft has been within 1 billion kilometers of it. No probe has photographed its surface or scooped its ice or flown through its ring. Every number in that inventory was extracted from data that began as photons, some from the Sun that bounced off Haumea's surface and travelled 50 astronomical units to reach a telescope mirror, some from distant stars that passed briefly behind the body and told us its shape in the timing of their silence. The method is the story. And the method deserves more than a passing mention, because it is genuinely one of the more remarkable things about modern planetary science. There is a tendency to think of knowledge as requiring proximity, that to know something well, you must be close to it, must touch it, or at least photograph it at close range. The history of Haumea is an argument against that tendency. Every major thing we know about it came from a distance of billions of kilometers, using instruments that were looking at something else and noticed something unexpected, or that were watching a precise celestial event and found more in the data than they had gone looking for. The occultation campaign of January 2017 was organized to refine the size and shape of Haumea. The ring appeared as a bonus, as the kind of bonus you get when the measurement is precise enough to see things the question didn't even ask about. Precision as a form of luck. Careful, patient, rigorous precision that creates the conditions for luck to become discovery. There is one more part of Haumea's story that has not yet been told, and it is a human story. A messy one. The kind that doesn't resolve neatly. The discovery of Haumea, who found it, who gets to say so, whose name goes on it, is a dispute that was never cleanly settled, and that lack of settlement is itself a piece of the history of this strange world. In late 2004, a team at Caltech, led by Mike Brown, was working through archival images of the sky looking for distant solar system objects. They identified something bright and unusual in data from 2003. A point of light in the outer solar system with properties that were obviously interesting. It was reflective, it was elongated in its light curve, and around the Christmas season, when they found it and started discussing it internally, they gave it an informal nickname. They called it Santa. The data sat, as data often does, while the team worked on confirming the discovery and preparing to announce it. Meanwhile, in Spain, at the Sierra Nevada Observatory, a team led by José Luis Ortiz was also searching through telescope archives, and in July 2005 they found the same object in their data. They announced the discovery. They submitted to the Minor Planet Center the provisional designation 2003 EL61, which was officially registered as the object's discovery record. What followed was complicated. Mike Brown's team pointed out that their own observation logs, including some information about the object they would later call Haumea, had been posted on a publicly accessible website. And that records indicated the Spanish team had accessed those logs shortly before making their announcement. The allegation was that the discovery announcement came after accessing priority data, not independently. The Spanish team disputed this. The argument became public and bitter in the way that priority disputes in science tend to become when careers and credit are at stake. The International Astronomical Union, the body that formally assigns names and discovery credits for solar system objects, stepped into a situation with no clean answer. They made a compromise ruling that was unusual. They assigned the formal discovery location as the Sierra Nevada Observatory, acknowledging the Spanish team's announcement record. But they credited no individual or team as the official discoverer. The credit field, in effect, was left blank. The object got a name, Haumea, and a classification, dwarf planet, formalized in September 2008, but no one got to put their name on it as its finder, at least not in the way that scientific convention usually allows. That is almost uniquely strange. Discoveries in astronomy almost always have names attached. Haumea's does not, officially, and the reason is that the process of attaching one became too contested to resolve. The name itself, though, is one of the more beautiful choices in the naming convention for Kuiper belt objects, which generally assigns names from the mythologies of peoples associated with creation, with distant places, with the underworld, or with the sea. Haumea is a figure from Hawaiian mythology, a goddess of childbirth, fertility, and the natural world, associated with the island of Hawaii itself. She is a figure known for her many children, for bringing life from her own body, for a creativity that expresses itself in multiplicity. The moons were named accordingly. Hiaka, the larger outer moon, is named for one of Haumea's daughters, a patron goddess of Hawaii Island and of the art of hula, a figure of warmth and skill and cultural significance. Namaka, the inner moon, is named for another daughter, a water spirit, a figure associated with the sea. The naming carries a kind of accidental poetry that planetary nomenclature sometimes achieves and sometimes doesn't. Haumea, the body, has produced things from itself. The moons may be its children in a physical sense, fragments of a collision or a disruption, or some violence that blasted material off the parent body and left it orbiting nearby. A family born from catastrophe, the way the Hawaiian myth describes a goddess who gives life in abundance. The collisional family members in the Kuiper belt, the dozens of icy shards on shared orbits with shared spectral signatures, are in some sense Haumea's extended children too. Pieces of the original body, or its ancient companion, scattered across a wide arc of the outer solar system, carrying the genetic fingerprint of their shared ice, and now the ring, close in, inside the Roche limit, where the tidal forces prevent anything from coming together, where material lingers in a kind of suspended state, unable to coalesce. That too is something Haumea wears as a trace of its history, a band of debris too close and too tidally stressed to ever become a proper child. Haumea, goddess of childbirth, surrounded by children she cannot quite release. There is something in that. The discovery dispute remains unresolved, not in any formal ongoing proceeding, but in the sense that the scientific community has not arrived at a consensus account that both teams would accept. Mike Brown has written about it. Ortiz and his colleagues have maintained their position. The EO's ruling stands, unusual and somewhat unsatisfying, giving the object a home at Sierra Nevada and giving the credit to no one. What this means for the history of outer solar system exploration is mostly a footnote. The science is what it is regardless of whose name is attached, but it is a reminder that the process of discovery is not always clean. Not always the lone astronomer at the telescope having the moment of recognition. Sometimes it is messy and contested and settles into a compromise that satisfies nobody fully. The universe doesn't care who gets credit. It just keeps spinning. And Haumea keeps spinning. That might be the image to end on. Or nearly to end on, a world 50 times farther from the sun than Earth, in a region of the solar system that is so cold and so far that sunlight there is about 2,500 times dimmer than it is here, where you are, listening to this. A world that receives the barest whisper of the sun's warmth, that carries on its surface a temperature of around 50 Kelvin, which is negative 223 degrees Celsius. Which is cold enough that most of the chemistry that drives biology has stopped entirely, where even carbon dioxide would freeze solid. A world that rotates once every 3.9 hours, which is to say that a day on Haumea lasts less than 4 of our hours, that the surface experiences a dawn every 3.9 hours, not that there is anything to experience it. Not that there is sky or warmth or anything to see in that pale, distant, barely there light. The spin is just a fact, a physical reality, a number the light curve handed over, and that has not changed in the 150 million years or so that has passed since the ancient collision that may or may not have imparted it. The egg shape holds. The ice surface persists, somehow fresh, somehow crystalline, when it ought by now to have been battered into amorphousness by radiation and cosmic rays. The 2 moons trace their orbits, Hyaka in her 49-day loop and Namaka in her shorter, more eccentric, more inclined 18-day path. The family members move on their related orbits, far enough apart that they will never meet again. Close enough in velocity and inclination that their shared ancestry is still legible in the geometry of where they are. And the ring, 2,287 kilometers out, 70 kilometers wide, particles in their 3-1 resonance with the body's spin, the Roche limit keeping them dispersed, keeping them a ring and not a moon, the ring turns, silent and unwitnessed, around a world that no spacecraft has ever visited, in a part of the solar system that exists, for most purposes, entirely in data. The January 2017 occultation lasted a matter of seconds for the main body. The extra dips that revealed the ring were briefer still, flickers in starlight that lasted perhaps a second or 2 each, the shadow of 70 kilometers of orbiting particles passing in front of a star several thousand light-years away. Those few seconds of data, recorded at 12 separate observatories scattered across Europe, were enough. Enough to locate the ring. Enough to measure its width and its radius, and, from the resonance calculation, to say something about why it exists where it does. Enough to write a paper, to publish it in Nature, to change the answer to the question of how many kinds of objects in our solar system can host a ring. All of that, from a few seconds of extra dimness in a star nobody but astronomers paying close attention would have been watching. This is what makes the story of Haumea more than just a catalogue of strange properties. The strangeness is real, and it is remarkable, the fastest spin, the egg shape, the crystalline ice that shouldn't be crystalline, the moons, the family, the ring. But what makes it worth sitting with is the method, the human willingness to watch, patiently and precisely, for the moment when a star blinks. To build instruments sensitive enough to catch a flicker of a few seconds' duration and extract from that flicker the dimensions of a ring around a world at 50 AU. To coordinate 12 observatories across a continent to share their data and pull a single coherent picture from it. To be willing to sit with uncertainty about the origin of the family, about what keeps the ice fresh, about who discovered the world in the first place, and to say, honestly, that the file stays open. That honesty is part of what science offers that nothing else quite does. The file stays open. The numbers might change. The 2017 occultation revised the size estimates and brought the density down from earlier values. A future occultation might revise them again. A future mission, if one is ever funded and launched and the decades of transit time accepted, might return images that overturn some of what the light curves and occultations have told us, or might confirm it in detail, or, and this is always the best possible outcome, might find something new entirely. Something that the shadows and the spectral lines couldn't see, something that requires the file to be reopened and amended. The history of outer solar system exploration is a history of exactly this process. Every close-up image from every flyby has contained surprises. Pluto had mountains and nitrogen glaciers and a heart-shaped plain. Nothing predicted any of that. Haumea, when it is finally seen up close, will almost certainly have surprises of its own. For now, we work with what we have. And what we have is not nothing. We have a world reconstructed from light, from shadows, from the precise timing of stellar occultations and the careful analysis of brightness variations in a point of light that takes 284 years to complete a single loop around the Sun. We have an egg-shaped world with a ring, 2 moons, and a family of icy cousins sitting in the cold dark at the edge of the region of the solar system we are still in the early stages of understanding. We have the ring, which nobody predicted, which arrived as a secondary dip in data gathered for a different purpose, which arrived as the best kind of discovery. The kind you weren't specifically looking for. There is something that the outer solar system keeps insisting on in every object it has offered up for study. Pluto insisted on it. Eris insisted on it. Arrokoth, the small contact binary that New Horizons visited on New Year's Day 2019, insisted on it in its own quiet way. And Haumea insists on it perhaps most emphatically of all. The solar system is stranger and more various than the models predicted. Every time a category was thought to be closed, planets are spherical, rings require giants, the Kuiper belt is a sparse and featureless disk, something has arrived from the data to open it again. The solar system keeps sending its own corrections. All we have to do is be watching when the star blinks. And the thing about watching is that it requires patience of a particular kind. Not the passive patience of waiting for something to happen, but the active patience of continuing to be ready. Continuing to maintain the instruments and the knowledge and the coordinate networks that allow a discovery like the 2017 occultation to be made at all. The 12 European observatories didn't gather by accident. Someone calculated the predicted path of Haumea's shadow weeks or months in advance, determined which locations on Earth would lie inside it, and coordinated the campaign. Someone kept the telescopes maintained and the detectors calibrated. Someone processed the data afterward, carefully, not letting the faint secondary dips get smoothed away by careless averaging. The discovery happened because people were paying attention in a highly organized and deliberate way. The luck was real, but the luck came to those who had made themselves ready to receive it. That is the thing about Haumea, and about the Kuiper belt, and about all of this. The readiness, the long preparation for a few seconds of shadow. The years of light curve data that preceded the 2017 occultation, building up the picture of the spin and the shape and the orbit so that when the shadow fell across Europe, the team knew exactly what they were looking at. Science, at its best, is the organized accumulation of readiness. The readiness to catch what the universe offers when it offers it. And it keeps offering. Out beyond Neptune, where the solar system grows thin and cold and strange, where the objects are mostly too distant and too dim to see with anything but the most dedicated instruments, where the bodies carry in their compositions and orbits the record of the solar system's violent early history, out there. There is still so much to find. The Haumea collisional family is the only confirmed one in the Kuiper belt, but there may be others. The ring around Haumea was not predicted, and if a ring can exist around Haumea, rings can exist around other trans-Neptunian objects as well. The crystalline ice problem on Haumea's surface has not been solved, but the solution. when it comes, will probably tell us something true and general about the processes that operate in the cold outer solar system. The moons and their excited, inclined, eccentric orbits carry a record of the collision or disruption that produced them, and when that record is fully decoded, it will tell us something about the violence of the early solar system that we cannot get any other way. Every loop that was opened at the beginning of this story has now been addressed, if not closed. The egg shape comes from the spin, from 3.9 hours being fast enough to stretch a body in hydrostatic equilibrium into a triaxial Jacobi ellipsoid. We know how to measure a world we cannot photograph through occultation timing and spectral analysis and the patient study of brightness variations. The ring is real, found in 2017, the first beyond Neptune, sitting in a 3.1 resonance at 2,287 kilometers out, inside the Roche limit where tidal forces keep it dispersed. The ancient collision is the best explanation for the spin and the moons and the family, but the mechanism of that collision remains contested, the exact shape of the violence still argued over by people who are better at orbital mechanics than most of us will ever be. The ice is fresh for reasons we don't fully understand. The dark red spot is there, probably, in some form, rich in something that absorbs at redder wavelengths. The two moons are the daughters of a goddess and orbit in paths that are their own kind of record. The family is real. The dispute is real and unresolved. The ring was there before anyone knew to look for it. The file stays open. That is the most honest thing to say. The file stays open, and somewhere far to the cold and the dark, the world spins, and the ring turns, and the moons move in their orbits, and none of it requires our attention to continue. It has been doing this for a very long time. It will keep doing it. We are not the point of any of this, and yet we are the only things, as far as we know, that have ever looked up and asked what that spinning egg-shaped world with the ring around it is made of, how it came to be, and what it might still tell us if we are patient enough and precise enough to listen. If there is something that Haumea, of all the strange objects in the outer solar system, teaches with particular force, it might be this, that the most unexpected discoveries come from the most careful watching. The ring was not in the model. It was in the data, waiting for an instrument precise enough and a campaign organized enough to find it there. The crystalline ice was not predicted to be fresh. It is fresh anyway, and the explanation will come, eventually, from someone who keeps looking. The egg shape, once you understand the physics, is obvious, but it took the light curve data of a moving point of light to reveal it. Everything we know about Haumea came from the gap between what we expected and what the measurement returned. That gap is where science actually lives. Take a breath. Let the numbers settle into something softer. 50 astronomical units, 50 times farther than the sun is from you. The light reaching Haumea's surface has travelled 8 minutes from the sun to reach Earth, and it keeps going, growing dim and cold, for another several hours before it touches that pale, crystalline, turning surface. What reaches Haumea is not really warmth, it is just photons, arriving faithfully, touching an icy world that does not need them the way we do. A world that has no weather, no seasons worth speaking of in human terms, no life, no one to notice the slow passage of its 284-year year. And yet we know it. We have given it a name. We have weighed it using the orbits of its moons. We have measured its waistline using the shadow it cast. On January 20th, 2017, we have found its ring in 2 brief extra dips in a graph of starlight. We have identified its family by the spectral fingerprint of water ice. We have argued over who found it first, and reached no consensus and moved on. We have done all of this from Earth, from instruments pointed at a point of light, using the only tools we have, patience, precision, and the stubborn conviction that the universe has things to tell us if we ask carefully enough. That is what Orbit Observer is here for, in the end. Not to give you everything resolved, everything neat, every mystery wrapped up. Because the universe doesn't do that. It gives you specific numbers in specific papers written by specific people using specific instruments on specific nights, and some of those numbers will be revised, and some of those mysteries will be deepened before they are solved, and some of them may not be solved in your lifetime or mine. But it is still worth knowing them. Worth knowing that an egg-shaped world spins once every 9 hours in the outer dark, that its ring was hiding in a star's shadow for all the years before 2017, that its 2 moons carry the names of a Hawaiian goddess's daughters, that its family of icy shards is the only confirmed collisional family in the Kuiper belt, that the ice on its surface stays crystalline in defiance of what the radiation environment should do to it, that no spacecraft has ever been there, and that everything we know came from light. Worth knowing and worth wondering about before sleep comes. If Haumea has stayed with you, if the ring surprised you, or the egg shape, or the way a few seconds of shadow can tell you the size of a world, I'd love to know which part of this landed hardest. Leave it in the comments, just a few words, just the thing you keep thinking about. Those small signals matter more than you might expect, and they help this channel keep going. There are other worlds out beyond Neptune, other strange objects in the Kuiper belt and beyond, each with their own unexpected properties, each with their own file that science is slowly opening. When you're ready to find out what else is spinning and tumbling and waiting in the cold, there's more here to watch. And if tonight was enough, if what you needed was a slow, careful trip to the edge of the solar system and back, then that's enough. Sleep well. The worlds keep moving, and tomorrow they'll still be there, still strange, still worth the attention. Good night from up here in orbit. I'll keep watch while you drift.